Next up, we have Dylan, who's going to be diving into some really interesting research, reverse engineering, mock handlers, IPC, some low-level internals. And so let's give Dylan a round of applause.
Thanks, everyone, for being here. Very excited to speak with you all today. Let's get this plugged in. We got a few slides to get through, as you can see, so looking forward to it. Just want to start by saying thank you all so much for being here. It's really a pleasure to be here myself. This is probably the most amazing, beautiful spot I could think of to have a conference, so thanks for Patrick and Andy and everyone for having me out here. Appreciate it. Quick bit about me before we get into the slides. I currently work at Google on the security engineering team, do product security reviews and proactive reviews on our products, as well as do 20% research with Google Project Zero, so trying to find vulnerabilities in other vendors' products. I was previously on the Mandiant Red team, so doing pen testing, proactive reviews there, and also spent some time doing reverse engineering with the Flare team. Perfect. So today, I'm going to talk to you guys about a really cool research project where I learned a ton going through this process. Also, I'm going to see if I can make this go full screen. Let's see. Oh, that's okay. All right, this will do. I'm going to talk to you about a project that I've been working on for quite some time now, writing custom fuzzing harnesses and looking at Mach IPC mechanisms on macOS and iOS. We're going to start with just a crash course on what fuzzing is, and specifically the Mach IPC system. Then we're going to go through the attack cycle that I kind of worked through during this process, then talk about some of the vulnerabilities discovered, and walk through some practical exploitation, show a demo that will hopefully work, and then leave some time for a Q&A at the end. So what is fuzzing? I like to define fuzzing as just sending unexpected inputs to a system in the hopes of making something unexpected happen. And throughout this research, I kind of tried to use this technique that I refer to as knowledge-driven fuzzing. So this is kind of a combination of automation, which is the fuzzing part. We're quickly identifying interesting inputs without understanding necessarily the base code. And we're using kind of the move fast and break things model. But then we're also incorporating manual analysis into the research. So using reverse engineering, using code coverage to tell us why our fuzzer is getting stuck, why is it causing strange errors, where is it bottlenecking. And I found this approach of a combination of fuzzing and also reverse engineering to be really effective in research. So the attack cycle that I worked through in this research was first finding a pretty interesting attack vector, choosing a target, creating a fuzzing harness, then using that fuzzing harness to produce crashes, look at those crashes, determine whether they're security relevant or if we just made mistakes in how we're writing the fuzzing harness, then iterate on that continually, and eventually hopefully identify relevant crashes and identify and exploit a vulnerability. So that first part, identifying an attack vector. As most of you know, exploiting a modern browser typically requires a second sandbox escape in addition to your RCE in the web browser process. And so IPC mechanisms are often a great natural bridge from that restricted and unrestricted, those two processes. And so they're commonly abused and a really nice technique that we can try to use here. There's some required reading here. Two of these articles are from Ian Beer, who's floating around here somewhere. Really nice previous work on using Mach IPC for heap grooming, as well as previous sandbox escapes and privilege escalation. I also used this blog post from Ret2 Systems, a methodical approach to browser exploitation, pretty heavily. It was really nice read. It's like a 6 or 7 part series, so definitely recommend checking this out as well. So talking a little bit about how Mach IPC works. Mach ports on macOS are basically an IPC message queue that's managed by the kernel. And in order to send to a Mach port, you need a port write. You can either have a send write, which allows you to send messages to it, or a receive write, which allows you to receive messages from that Mach port. And just to give you a brief idea of how we might establish a Mach IPC connection, there's this concept of a bootstrap server. This is a special Mach port, which helps establish connections with other Mach ports. And by default, every process can send to the bootstrap server. They all have a send write to it. So you might have a Mach service with a name that's registered with the bootstrap server. Say it's com_apple_obts. And then let's say Alice allocates a new Mach port with a receive write. She's then going to register the name com_apple_obts. She's giving the bootstrap server a send write to the port that she has a receive write to. Then Bob comes along and he asks the bootstrap server for the service named com_apple_obts, and the server gives Bob a copy of that send write. So then Bob can send messages and Alice can receive them. That's how we establish this Mach IPC connection. Cool. So now we have a little background on how this IPC process works. How do we actually choose a target that we want to fuzz and try to find vulnerabilities within? System daemons were a very interesting target. They typically run with elevated permissions. They have a lot of access to the file system, so they're generally a good place to look here. And they have a lot of IPC services and messages that they're sending constantly. So system daemons are registered with Mac using launchd. There's plist files depending on whether it's a user or system daemon in the two directories that you see here. And we can see just an example of the address book Mach service that's registered here in a plist. So what I wanted to do is kind of slim down the list of system daemons that we could take a look at and try to find ones that would be interesting to attack from a sandbox escape perspective. So we start with kind of all macOS processes, then looking for ones with a Mach service, and finally ones where a sandbox rules were actually allowed to send IPC messages to that system daemon. And this is important because we want to look at high-profile applications like web browsers and Adobe Acrobat, for example, Microsoft Word, things where people are using these all the time, and then find services they can send IPC messages to. That's how we find really impactful sandbox escapes. And then we identify the binaries that implement those Mach services, and we start fuzzing them. So to find these sandbox-allowed communications, I think it was just touched on in the last talk a little bit about these sandbox configuration files, and they use this tiny scheme format. So you can see here, this allow Mach lookup directive tells you that a given process is going to be able to send IPC messages to that Mach service. So then if that process is interesting, that service might be interesting to fuzz. I used the SB tool utility, which I believe was created by Jonathan Levin, who's also around here. This is really helpful. I modified it a little bit. Basically uses the sandbox check API to determine which Mach services a process can send to. And so it'd start with a process like Safari, run the SB tool and look at what Mach services it could send messages to. And then I had a pretty nice list of targets for potential sandbox escapes. Eventually, I chose to select coreaudiod as the service to target here. And there's a few reasons for that. It's a pretty complex service, a large binary, lots going on. It allows Mach communications from several impactful applications, including the Safari GPU process. And it had a large number of Mach message handlers. So a lot of potential attack vectors and entry points here. It also seemed to allow control and modification of audio hardware, which would likely require elevated privileges. And then finally, the coreaudiod binary and framework are both closed source, so it would be a unique reverse engineering challenge. Cool, so the next step was to create a fuzzing harness, which most of you have probably heard of a fuzzer. A fuzzing harness is basically code that you write that allows you to send input from that fuzzer through an attack vector. You're basically just calling a desired function, and you're taking that fuzzer input and you're redirecting it into a very specific spot. This helps us fuzz. You can really write a harness to fuzz anything, anywhere in code. And this is where we start to find vulnerabilities when we get very intentional about our fuzzing harnesses. So the entry point really matters when we're writing a fuzzing harness. Fuzzers can find a whole lot more than surface level bugs, and especially if it's coverage guided, so it's getting feedback on how it's doing from the binary that it's fuzzing. But really, it's only going to be effective if that energy is focused in the right place. And the right place to fuzz is a bit of a loaded term. It's a lot of trade-offs that you're weighing. You're looking at the ease of developing a harness versus is this actually realistic to how the environment or the binary that I'm fuzzing is operating. You might be weighing trade-offs in performance versus like more false positives or less false positives. So it's highly dependent on your target and research goals. I had a couple of different options for the ways that I could construct my fuzzing harness here. The first way, which seemed kind of the most easiest to me, was to use the Mach message API. So this is the typical way that you will send Mach messages through the system. And basically what we would do here is we would write a fuzzing harness, which was just call the Mach message API with our fuzzing input, send it via Mach IPC, that would be processed by the kernel, and then it would end up in our Mach message handler. Then if we got a crash, hopefully we would know that there's something interesting to look at there. So this is very simple to write a fuzzing harness for, and it's also very similar to how the end exploit will look if we find a vulnerability. But there are some cons to this. It's going to be very slow. The kernel is going to have to process each of these messages, and when we're fuzzing, we do care about performance because it helps us find things easier. There's also a lot of points of failure in this system, and the biggest thing is probably we're dealing with two different process address spaces. So getting code coverage from our target process, the receiving process, becomes a lot more difficult here. And we really need that code coverage to identify how the fuzzer is doing and make progress. So the other option would be to use a direct harness. And so this would involve loading some code that's implementing the Mach message handlers, and then calling those handlers directly with desired input. Now this is a little bit trickier to implement, but the pros are it's very, very fast. We're just dealing with one process. We're in the same process space, so getting instrumentation and code coverage becomes much, much easier. And also, it's very easy to know which input caused the crash and replicate, as opposed to sending it through the kernel and trying to figure that out. It is going to be a little bit different potentially from the end exploit. So when your fuzzing harness is deep hooked up into code, you might not be able to call that function or that input directly. You might have to backtrack a little bit and understand how to actually trigger it. And we also might have to invoke specific initialization routines that would normally be invoked if we were calling the handler legitimately. So I chose this approach for fuzzing due to the pros that we mentioned here, mostly because of the same process space here. So the direct harness approach would be to first identify the function that processed incoming Mach messages, so that would require a little bit of reverse engineering. Then write a fuzzing harness to load the message handling code from coreaudiod, use a fuzzer to generate inputs and call that the fuzzing harness, and then hopefully generate some crashes that we could exploit. So the first thing was to find this Mach message handler. Where was the processing of these incoming messages actually happening? I looked in the coreaudiod binary, and there were no references to this Mach service that we saw, this audio hal d service. So that was interesting. But there was a reference to this framework, this CoreAudio framework, so I thought most of the logic might be implemented there. But then I couldn't find the CoreAudio framework on disk. And some of you might know about this, but starting with Big Sur, most framework binaries are not on disk, they're in the DILD shared cache, and so we need to extract them. There's some good tools out there for extracting DILD shared cache binaries. I used the one linked here. You can also pass the DILD shared cache directly into IDA Pro or Binary Ninja, and it does a pretty nice job parsing it for you. So now we were able to see the actual logic that was handling our incoming Mach messages. You see right here in the CoreAudio library, it's actually registering that audio held service, which we want to interact with in fuzz. So that's cool. The next thing for finding the processing of the messages was learning about MIG subsystems. So many Mach services use this thing called the Mach Interface Generator, or MIG. This is a type of interface definition language, and it abstracts away a lot of the Mach layer for developers. And so it makes it much easier for them to use, kind of write in higher level interface definitions, and it's implementing kind of all of this Mach sending and receiving under the hood for them. So you can grep pretty easily if you're looking at a Mach binary for these subsystems. Right here in the CoreAudio library, you see two subsystems listed for the client and the server. We're going to want to look at the server here. So diving into IDA a little bit to look at the how this is composed, we see basically what's a function lookup table. We have an incoming message here, which is passed in the RDI register. It's grabbing a message ID from that incoming message, and then indexing into a lookup table to get the actual offset for the function, the message handler that it's going to call. And then we end up calling one of the RPC functions that you see here. Typically, these are going to start with a _x if you have symbols available. So those can be nice for enumerating the different Mach message handlers that you can interact with. And now we're starting to understand some of the APIs that we have available and some of the things that we can try to fuzz to potentially cause crashes. So the next step, now that we found where this Mach message handling was going on, was figure out how to call this message handler, because it's not going to be exposed as an API. It's not exported. So I borrowed some logic from Ivan Fratrick, one of my colleagues, and his tinyinst library. I'll definitely talk about this more on in the talk. But basically, it parses the Mach-O binary headers and load commands, extracts the symbol info, and then you can use it to resolve and call the target function. So this is pretty cool. Now we have a fuzzing harness where we can directly call that Mach message handler code that we found through our reverse engineering. And this fuzzing harness and all the code that I'm going to be talking about today is open sourced in the Project Zero Tools GitHub repository. So feel free to take a look at that. Cool. So now we can call this Mach message handler, but we need a good corpus. We need a good set of inputs which we want to fuzz through this Mach message handler. So I wanted to find a way to harvest legitimate Mach messages, and a really nice way to do that was to write a quick little LLDB script to hook onto that message handler, and then find some applications that would interact with it. So the audio MIDI setup application on macOS was pretty helpful, because you can create and modify audio devices on your system. And so I just started playing around with that, looking at all the traffic that was getting sent, and basically dumping all the Mach messages that were sent through there. Cool. So now we have a way to call our Mach message handler and a corpus of inputs. Now it's time to actually fuzz and produce crashes. So I used the Jackalope fuzzer, which is also written by Ivan Fratrick. It's really nice. It has a high level of customizability. You can define custom mutators, instrumentation, or ways to deliver your sample. And I think the biggest thing, it works really nicely on macOS. And it provides code coverage for binary-only fuzzing, which was going to be important for us here. We don't have the source code. We need a way to get code coverage, and so we need some sort of dynamic instrumentation, and tinyinst is a really nice lightweight way to get that works out of the box with Jackalope. So I started using this setup with the custom fuzzing harness I wrote, and immediately we started getting crashes. And I was like, this is awesome. Let's go. We got something. But no, this is pretty common. Initial crashes that you get are often not security relevant, and oftentimes they're indicating either a fuzzing harness design issue or some sort of invalid assumption that you made while interacting with the service. So it's probably your bug and not the developer's bug, at least early on. But that's why we iterate on the fuzzing harness. So we have something, we have a way to deliver messages, there's something going wrong, let's see if we can figure that out and make it better. So one problem that I had initially was initialization. The fuzzer and my fuzzing harness neglected bootstrapping and initialization of tasks. So you can see on the left here kind of what my fuzzer and harness is doing. It's just immediately calling the mock message handler, whereas on the actual macOS system, the coreaudiod process is going to do, initialize some global variables, set up hardware, perform other initialization routines, and then call that. So we definitely need to take that into consideration with our fuzzing harness. And along with this, code coverage becomes very, very helpful here. So you can see here loading the code coverage generated from TinyInst into IDA Pro with Lighthouse. We can really quickly start to see kind of what's going wrong with our fuzzing harness. The green is lighting up. We're always going down this path. We never get to the bulk of the logic going right. And so we might then want to take a finer look into why is that branch condition always going that way? Is there a way that we can structure our fuzzing harness to help guide the fuzzer past that bottleneck? Another bad assumption I had, in addition to the initialization, was that all mock messages functioned independently of each other. And you can see pretty clearly in this log that that was not the case. So we send a set property data function, and it responds, there is no client. So that's clearly starting to hint at maybe we need to call some other function to initialize a client before we start trying to set data. And this really highlights the need for structured fuzzing. This is a concept where most fuzzers only accept bytes, so you pass them a bunch of bytes, or the fuzzer will pass you bytes, and then you'll send that to the thing you're fuzzing. But what if we actually consume those bytes and then did something a little more clever with them? I highly recommend you check out Ned Williamson's 2019 OffensiveCon talk if you haven't before, but he talks about this idea really well, this idea of structured fuzzing and turning stateless fuzzing into stateful fuzzing, which is going to be really important. So I like to call this approach API call chaining. So we have all of these mock message handlers that we can call, and we know that calling them kind of just calling one and then seeing what it does is not going to work because they're dependent on each other, right? So what if instead of just doing that, we add a simple while loop up at the top, we take the data that's coming in and we just keep looping through, and while we still have data, we call a different mock message handler. And then we see what happens, and we keep going until we run out of data. Now, this might seem like a pretty simple technique, and it is. It's not very hard, but it is extremely powerful when you give the fuzzer that sort of empowerment to explore these stateful interactions with each other. The code coverage and the coverage-guided nature of the fuzzer will then start to explore the interactions of these different APIs, and all you basically did was give it a while loop. So it's very, very powerful when you have these sort of stateful APIs that you're trying to fuzz. So this gives you kind of an idea of basically what my fuzzing harness was implementing here. And once again, the whole thing is open sourced. Cool. So another thing that happened here was the fuzzer would start getting stuck, exploring functionality that wasn't really relevant, or we didn't really care about it exploring. Sometimes this was buggy or unneeded. For one example of this, it's trying to call bootstrap check-in to register the audio HALD service, but it was already registered by the legitimate coreaudiod, so this throws an error early on. This is pretty easy. We can use some function interposing and just write our own version of the bootstrap check-in function, have it return current success, and give it some arbitrary port. So you kind of get all these little weird things happening because you're just injecting data into a process that is supposed to be running in a more complex system. But you can start to mock out some of these things to really focus on what you care about. Another thing that happened is there were a couple of bugs that I identified in some of the routines that were not security relevant at all, but for example, there was no null check when I was trying to pass a property list to one of these APIs. And so we would end up getting a null dereference here. And this was really slowing down my fuzzer because it would keep exploring this path. And it started to get really annoying because it would just bottleneck here and not progress at all. So what I ended up doing here is using that tinyInst hook API that I mentioned earlier. It's basically a way to define some custom code that's going to fire when you enter a function of interest and also when you're returning from a function of interest, similar to Frida, but a bit more lightweight. And basically went ahead and just patched this null dereference myself and added it to my fuzzing harness. And those modifications that you see with the fuzzer here, those are also in that same repository. You can check them out if you like. Cool. So we had to deal a little bit with some of the intricacies of fuzzing something that's outside of its native system, but we worked through most of those obstacles, and now it was hopefully time to identify and exploit a vulnerability. So just to give you a brief background on this service that we were fuzzing, it's making up the hardware abstraction layer on macOS, and this basically allows you to interact with audio devices and settings on the operating system. So this information gets stored on the heap. It's a linked list of these halls objects, and so I wrote a tinyInst hook to go ahead and find where that linked list was stored and then dump all of them. This was really helpful for figuring out what was going on and when eventually crafting an exploit. So you can see one of these objects here, the system object. Additionally, when you're looking up or modifying a halls object, or rather when the API is looking up or modifying, the CoreAudio APIs use this thing called copy object by object ID. You pass it a uint, and it returns back a pointer to a halls object. So this was an important thing to know as well. So the first intriguing crash that I came across was in this, this message handler, this IO context fetch workgroup port call. And it was a super shallow crash, as you can see here from the stack trace. That frame number 1 there is the actual message handler, or the indexing lookup. And then the fetch workgroup port is like the message handler itself. So it's super shallow crash, and it's actually crashing on a call instruction. So this immediately looked really, really interesting to me from an exploitation perspective. As I looked into this more in IDA, I found out that the RAX register was getting derived from a call to that copy object by object ID function. So it would fetch a house object from the object map from an ID that was passed to it, and this was actually user provided from the mock message. And then it would dereference the address A1 at offset hex 68 of that halls object, dereference address A2, so a second index into that, at offset 0, and then call the function pointer at that offset, 168 hex. So there's a little bit of pointer indirection going on here. Looks like maybe a v-table lookup going on here. So to visualize this a little bit better, what was going on legitimately, and then maybe how we might try to weaponize this, we have an expected object here. It's expecting this IOCT object, this IO control object. Then there's a dereference happening at offset 68 into some other object where there's a v-table lookup. It's calling some function, maybe get port, and that function call happens. What if we were able to use some other object and pass some pointer that we could control here, have it point to a fake object with a v-table lookup that then calls our own function? So that's kind of the hopes for the exploitation that I had here, was to try to find some way to write to this offset hex 68. So I reported this to Apple on October 9th, 2024. Just to let you guys all know, this has been patched. It was fixed on December 11th. I feel like normally Apple likes to downplay the severity of CVEs, but here they actually upgraded it. They said that you could execute arbitrary code with kernel privileges. As far as I know, that is not possible. You can definitely do it as root, but they might know something that I don't. So that was kind of interesting. Cool. So let's dive back into this exploitation strategy here. I wanted to try to find a way to write data into this offset hex68 within any house object. If we could do that, we could start to control this dereference chain of pointers and maybe get our own function called. So there was several places that we could do this, looking through the APIs in IDA. When creating a new audio device, for example, there was a UID that you could specify in your Mach message, and it would create a CF string at that hex68 vulnerable offset. So this looked like a pretty cut and dry way to maybe exploit this, but it did not work out because, if you remember, what we're doing here is we're dereferencing offset hex68, and then it also dereferences at 0 index the result of that. And the CF string type has an uncontrollable header. It's the CF runtime base thing right here. So we actually couldn't control that. And a raw CF string was not going to work for our purposes. So we would need to write a pointer to an object that we controlled. And then that object would in turn point to data that we control. So it's a little bit more tricky of an exploitation primitive. One thing that a couple of my colleagues offered up as a suggestion is running coreaudiod with guard-malloc pre-scribble. So what this does is it'll place hex AA bytes in every freshly allocated block of memory. Very useful, because then you can tell when objects are not getting zeroed properly or they're using uninitialized memory. And sure enough, as I started doing this, I identified an object, this engine object you see here, that at our vulnerable offset hex68 was using some uninitialized memory. And in particular, it was these 6 high bytes, which were using uninitialized memory. So you can see them here. Here's us re-triggering that vulnerability. And the RDI register, you can see, is using that uninitialized memory. So we have a new exploitation strategy here. We need to find a way first to allocate an engine object. We have to figure out how to create it and get it stored on the heap. We need to find a way to allocate a bunch of data we control and spray it on the heap. And then we need to create this chain of indirect pointers to that controlled data. Then we need to get our program to reuse our indirect pointers in the unclaimed memory region when allocating our engine object. And the caveat here is that the indirect pointer that we start with is going to have its last 2 bytes zeroed out. So a little bit tricky, but it might just be crazy enough to work. The first thing was I needed to find how to create this engine object. Eventually, through a bunch of reverse engineering, I did find a way. Basically, you call this get property data API by sending a message handler. You tell it that you want to create a tap, which, from my understanding, is as a legitimate developer, you would use this to look at an audio stream and maybe copy it and perform some sort of modification. So a lot of like audio, maybe like Fruity Loops or other music development software might legitimately use this API. But then one of the things it did is it created this engine object as part of that process. So you can see it right here. It's allocating 776 bytes, and then it is creating that IO engine object that we care about. So one little problem showed up after I started allocating these objects, and that was that this object was only 776 bytes. And if you know a little bit about the Apple heap allocator, there's different memory regions that are used based on the size of the allocation. So we were at 776. We were in this tiny region here. One of the things with the nano and tiny region is that calloc will be called, so it's going to zero out the memory during the allocation. That doesn't happen for small, medium, and large, but unfortunately for me in this case, it did. So even if it was using uninitialized memory, it would get cleared before the new object was instantiated. So that was a bummer, but then I kept looking, and there was another way to create an engine object, and this time it would get allocated with 1152 bytes. So that would be in that small malloc region, and it wouldn't actually get cleared out before we used it. The problem was, though, to instantiate it, you needed to create an audio plugin, and in order to do that, you needed to be able to place into a root-owned directory, which we would not have here in our sort of Safari RCE scenario. But looking into these naturally occurring engine objects a little bit more, I was wondering, could we use one of these objects that's already created to reuse our sprayed data? And the thought here was, since system daemons on macOS continually restart, if you crash one, it's going to keep restarting. We kind of have unlimited tries here to try and get our data into one of these existing engine objects and then have it use it. So cool. This is a potential way to go about things, but we need to find a way now to allocate data and spray it onto the heap. A really common thing that we like to do in macOS exploitation is use property lists for this. There's a lot of Apple APIs that will accept user data either as a binary or XML serialized property list, and then they'll deserialize that data, allocate new memory as core foundation objects, and store it on the heap. So that's exactly what this function that you see here was, and we could call this by sending a mock message. So that's a great way to, a great allocation primitive that we can use. So the property list data actually got stored in memory, and then also, interesting enough, it got stored on disk at the plist that you see mentioned here. And then it would get reloaded each time coreaudiod restarted, which was something I took note of. Another reason that I wanted to use property lists for this specific exploitation was the indirection that they would offer here. So we can nest different core foundation types in property lists and create that indirection that our pointer chain needed. So a CF array or a CF dictionary would allow us this indirection, and then the CF string or CF data types could be a great option for actually storing our payload data, our ROP chain. And you can also specify a huge number of elements forplists. So it's a great way to mass allocate data if you need to do that as well. Okay, so our new updated exploitation strategy here, we're assuming, of course, since we're looking for sandbox escapes, that there's an RCE existing in maybe a web browser. And so that's outside of the scope of this research, but looking at the sandbox escape, we would call this set property data plist function, call it multiple times, and pass a plist containing 1,200 CF string objects. I figured out this was the right amount of objects to allocate each time through a lot of trial and error. Then we would trigger the type confusion vulnerability, and this would just be to crash and restart the process. And then we would hope that an engine object got allocated with our old plist that got freed. Then we'd try to trigger the type confusion again on one of the engine objects. We'd pick one at random, and then hope that it would use our pointer chain that we set up through the allocated plist. And then we just keep on repeating steps 3 and 4 until hopefully it will work. To show this visually, since it's a little bit hard to visualize just in your head, we would allocate all of these CF strings in an array through our plist, and then each of these would point to a different CF string, and then there'd be a pointer here, offset 16, that would point to our raw data, and this is where our actual ROP chain would exist. Then we would hope that when a engine object got allocated, when coreaudiod restarted, at offset 68, normally it would be pointing here to this CF string object, but since we're actually getting the last 2 bytes zeroed out, we would hope that it would point to this raw bytes pointer, and then it would dereference that and get to our raw data that we specified. So there's a little bit of hoping involved here, and actually the clearing out of those last 2 bytes kind of ended up helping us with this exploitation primitive, because otherwise we would have ran into the same issue where we were just pointing to the CF runtime base header. So this might just be crazy enough to work, and certainly enough, you can see here, I wrote a object dumper script, once again using tinyinst, and you can kind of see what this chain looks like when it's all set up correctly. So at offset 68, we have a pointer. That pointer gets dereferenced to this object, and it's actually the start of one of the allocated strings that we have here. So now, the next step was to build a ROP chain. This is what the ROP chain I ended up using looked like. One important thing to note here, ASLR does not come into play because we are just restarting the same CoreAudio daemon, and it's loading libraries from the DILD shared cache. So we actually can just keep using that same ROP chain each time, which is really nice. So we start with a stack pivot gadget, and then move through. For this example, we're just opening a file that normally coreaudiod would only be able to open in this library preferences audio folder. One thing I also learned and had to deal with was encoding things properly. I had to send the data in the plist as UTF-16. Otherwise, the UTF-8 bytes would be outside of their range and break things. So just another note. UTF-16 is really nice for these types of exploitations. Cool. All right. So let's see if we can maybe get a demo to work here. Right now, I'm in the library preferences audio folder, just to show you what's in there. This is owned by coreaudiod, which is a privileged user on the system. And then also just note, this is that plist that I mentioned that we're going to be sort of modifying here. It's pretty small right now. It's going to get a lot bigger. Cool. And then what I'm going to first do is, this is allocating basically 20 plists, and then in each of them there's going to be 1,200 CF strings with our payload inside. So this will take maybe a minute or so, but it's just going to create this what's called a meta device. It's going to pass our plist along with it, and then that is going to get stored in this plist on disk as well as in memory. So it's starting to get pretty big here already. Let's see, we're going to do 20 of those, and also just to show you kind of our payload getting stored in this plist. Let's see if we can see it. So you see all these strings. These are going to start including our payload. Perfect. Let's see if this is done. So we're at allocation 16. Actually, I might open this with Vim to give you a better idea. Okay, there you go. So there's all of our data looking really, really nice, rendered as ASCII. And maybe I'll just kill that. Cool. So the exploitation or the allocation piece is almost done here. Every time we get every once in a while we will get an error with creating our meta device, but we still have a pretty large plist here. Oh, whoops, that's the wrong directory. It should work though. It's probably around like 39 megabytes stored on disk. And then what we're going to do is I just have a shell script that's going to loop. And what this is going to do, it's just going to try to trigger the type confusion. It's going to pick a random engine object and then try to exploit it. And then hopefully everything lines up and it will write our payload to the directory that we shouldn't be able to control. So let's run that. So this may take anywhere from 1 to 50 tries. Typically that's about how long it takes for me. So we'll see if it works in the first couple of tries. If not, I have a couple more slides and then we can come back to this. But it definitely is not a super sexy exploit. It takes a few times to run, but hopefully we'll get to see it work on stage here. All right, I'm going to go back to my slides. I do have a video as well, which we can revert to, but we'll let it run in the background here. Additionally, I did want to mention one other vulnerability that this fuzzing approach and fuzzing harness found. So this was a double free vulnerability I found in the same service as coreaudiod, same sort of API call chaining fuzzing technique. And this was patched on May 12th, so a bit more recently. There is a published write-up that I did, which you can find in the Project Zero bug tracker. Cool, and then just to mention a couple of blog posts about this research, while we let the exploit hopefully keep running. I published part 1, which talks about everything that we talked about today in more detail. So building the fuzzing harness, going through kind of that whole process of reverse engineering and finding out what to target, and then the vulnerability itself. And like I mentioned, the tools, so the fuzzing harness, the custom instrumentation, and a POC for this crash is available in the P0 tools repository. I'm also working on a second blog post, which will probably be coming out in the next few weeks. And I'll be releasing the POC exploit that I'm showing you right now along with it. So hopefully you can get it to run on your system as well. Cool. Let's just look back if we've had success yet. We have not. We're going to let it run a little bit more. Perfect. But hopefully what I've done today is show you the power and importance of sandbox escape vectors and how powerful IPC mechanisms can be. I hope I've sold you on this approach of knowledge-driven fuzzing for vulnerability research and shown, in theory, how you would exploit a type confusion vulnerability in coreaudiod. And I hope I've inspired you to perform some security research of your own. I'd like to give a huge thank you to Ned Williamson and Yvonne Fratrick as well. They were fantastic partners in helping guide this research and bounce ideas off of, as well as my wife Isabel, who's joining us today. So thanks for putting up with all of the late nights doing this research. And with that, thank you. You can follow me on Twitter, read my blog, and let's see if we've had success here. So not yet. Looks like the demo gods are unfortunately not with us. I'll go ahead and go to our video, which is basically going to look a whole lot of like what we're doing here, but we're actually going to have success at the end. Let's get to the end here. Oh, did we get it? No, we did not. Cool. So it should write to that preferences audio library, that preferences audio folder. We're on the unlucky side of things, it looks like here. But in the meantime, when we let this run, I think maybe there's a couple minutes for questions. Perfect. Any questions are welcome.
Would
Yeah.
Apple's new memory integrity enforcements, if they brought this to the macOS, would that impact this?
Yes, absolutely. That's a great point. And yeah, Patrick was asking about Apple's new memory tagging enforcement. And it's important to note here, this was all done, this exploitation and research was done on an Intel machine, as I'm sure you've seen. So it didn't deal with PAC at all here, kind of none of the new memory enforcement features. But yeah, this would make it considerably trickier to exploit for sure. Yeah.
What would you recommend Apple do? Like, should they fuzz more?
Yeah.
Project Zero?
Yeah, that's a great question. I didn't go over, yeah, I think that's a great question. So I think in cases where you're dealing with fetching objects off the heap and they're kind of user-controlled indexing, there needs to be sort of more checks into the actual type that is expected. And that was basically what the fix looked like. They added a lot more strict type checking. All that type information was stored in the object, so it was pretty easy for them to implement. But yeah, I think, yeah, just stricter type checking in this case is going to help prevent this. But yeah, definitely more fuzzing. I think, especially where you have these like stateful APIs, exploring them as we saw, it requires a little bit of legwork and typically some custom fuzzing harnesses. But if you put in that work, it will typically yield great results.
And then they could use that for other fuzzing.
Exactly, yeah. Yeah, cool. Any other questions? Oh yes, right there. Yeah, you're asking about the instability. Is there any way to make the exploit more stable? Yeah, for continually crashing the process, yeah. So this was, every time that we trigger the type confusion and it doesn't go to our exploit chain, we get that, that call crash that we saw, the initial crash. So it's gonna crash if we're not successful, and that's just kind of an unfortunate part of how the exploitation works. But luckily, like, it's a system daemon, so we can just continue trying it until hopefully it works. Today we're getting a little bit unlucky, but we'll let this run in the background, and maybe at tonight's session it'll be ready. Awesome. Thanks, everyone.